Good morning friends. Last we discussed about the central maxima, first order minima, and also we derived the condition for nth order minima, and also we derived the condition for nth order secondary maximum in terms of angle and also in terms of the path difference. So here the diffraction is also completed. Now, what is the graph of the intensity of the fringes obtained in Fraunhofer diffraction versus the angle of diffraction? Already we discussed in diffraction theory is the angle of the wave emanating from different part of the wave front. The angle is increases with the MC line. So different maxima and minima are obtained. So as a result, on the screen, the different points are bright and dark, and also the intensity of all the bright are not same, and also the width of all the bright points or the fringes are not same. So here we are going to discuss about the graph of the intensity of the light versus the angle of diffraction for Fraunhofer diffraction. For that purpose, first we do the graph. The graph is like this manner. Here, the intensity is taken on the y-axis. Intensity of the light is taken along the y-axis, while the angle of diffraction is taken on x-axis. Angle theta, this side and also this side, theta. Now the central maximum has the highest intensity and also the highest width. And already we know that for first order maxima is formed due to only 1/3 part of the wave, 1/3 part of the slit, which wave produce the intensity at point P. Therefore the intensity of the first order secondary maxima is only 1/3 of this. Now next is the 1/5. So this way the intensities are obtained. That means decreases with increase in angle of diffraction. So there is the graph of intensity versus the angle of diffraction. Angle of diffraction. Now here we have to discuss this thing. That is the maximum. I maximum. There is the zeroth order or the central maxima. There is the first order maxima on either side of maxima. Okay. The graph of intensity of light versus angle of diffraction for Fraunhofer diffraction is shown in figure. From the graph, we are going to return the characteristic of this. First, the intensity and width of central maxima is highest, and intensity and width is decreases with increase of the angle of diffraction, and intensities and width decreases with increase in angle of diffraction or increase the order of diffraction Now, diffraction depends on ratio lambda upon A. Ratio lambda upon if lambda upon A is less, the diffraction is less, and if lambda upon B ratio is more, the diffraction is more. Now the intensity of the central maxima is maximum. Next is now the intensity of central maxima or the maximum is highest. The angular width of next is the angular width of central maxima is inversely proportional to the width of a slit. So these 4 points are the characteristic of the graph of intensity versus angle of diffraction in front of a diffraction. Again, here the graph of the intensity versus angle of diffraction is shown. From the graph we can say that for central maxima, the intensity and width of central maxima is highest. As the order of diffraction increases, that means the angle of diffraction increases. So what's happened? Here the width and intensity of the line is going to decrease. After that, the intensity is maximum for the central, that ranges to the central maximum. Now, one more thing, the diffraction depends on the lambda upon A ratio. If the lambda upon A ratio is less, the diffraction is less. And if the lambda upon A ratio is more, so the diffraction is also more. And the angular width is the of a central maxima is inversely proportional to the width of a slit. That means if the width of a slit is decreased, therefore the width of a central maxima is increased. Already we know that in front of a diffraction, that is the width of a slit, and here the screen, that is slit. That is the width of the slit, that is the small a. There is the perpendicular bisector of the slit on the screen, that is the C. So here the first order or the central maxima is obtained. That is the first order maxima, second order. So on either side of this both. So that is the half angular width, and that is the total angular width. Angular width of a central maxima is the distance between the first order minima on either side of central maxima. There is theta, there is also theta, so there is the 2 theta. There is depends on the width of a slit. Clear this thing? So that is the characteristic of this graph. Sometimes the 2 marks question may be asked. State the difference between the interference and diffraction. Now, in this type of the question, each and every point gives you the half marks, that means the 0.5 mark. And due to that reason, at least we have to add down the 3 points or the 4 points for each part, interference and diffraction. For that purpose, we take the interference in this side and diffraction in this side. Okay. How the interference is obtained? The interference is obtained due to the superposition of the waves emanating from the different coherent sources. Because for the interference, the coherent sources are required, and from these coherent sources, the waves are produced, and these waves superpose on each other, and interference is formed. Therefore, it is obtained due to the superposition of waves emanating from different coherent sources. While in diffraction, it is also due to the superposition of the waves, but these waves are produced from different parts of the same wavefront. It is obtained due to superposition of waves emanating from different part of the same wavefront. Now the next second is dark and bright fringes are of equal width in interference. Bright and dark all fringes of equal width. Now here, the width of the central maxima is maximum. The width of the all fringes are not of equal width. All fringes are not of equal width. The width of central maximum is highest and width of the fringes decreases with decreases with increase in order of diffraction. So these are the 2 points. Now one more points about the intensity. About the intensities of interference and diffraction pattern. Here again the interference and this side diffraction. Third point is that the intensity of band fringes are equal. All band fringes are of equal intensity. Now here, all band fringes are not of equal intensities. Intensity of fringe or the intensity of central maxima is highest and decreases with increase in order of diffraction. Now, fourth point. All dark fringes are perfectly dark. All dark fringes are perfectly dark. Now, in diffraction, the region of minimum intensity is not perfectly dark or completely dark. The region of minimum intensities is not completely dark. Not completely dark. So, friends, there is the difference between the interference and diffraction. Again, we revise it. Here, the interference pattern is formed due to the superposition of the wave. But these waves must be emanating or produced by the two coherent sources. Again, in interference, it is obtained due to the superposition of the wave. This wave must be emanating from the different coherent sources. While in diffraction, it is also obtained due to the superposition of the wave. These waves are emanating from the different part of the wavefront which is incident on a slit. Now next, bright and dark, all fringes of equal width. Width of all the fringes, either dark or the bright, are same in interference. While here, the all fringes are not of equal width. The width of a central maxima is highest and the width of fringes decreases with increase of order of diffraction. Now next, the same way about the intensity. All bad fringes are of equal intensity. While here, all bad fringes are not of equal intensity. The intensity of the central maxima is highest and decreases with, or the intensity of the other fringes decreases with increase in order of diffraction. Now the point at which the dark fringes are formed in interference is completely dark or perfectly dark. But the black spot is obtained at the position of dark fringes. While in diffraction pattern, the region at which the minimum interference, that means the dark fringes formed, is not completely dark. So there is the difference between the interference and diffraction. Now after that we are going to discuss about or derive the formula of linear width and angular width of, first we derive for central maxima and then we derive the equation of angular width and linear width for nth order secondary maxima. Clear? Okay. Now for that purpose here, the distance between or the linear width of a central maxima is the distance between the first minima on either side of the central maxima. Now the angular width of a central maxima is the distance between first minimum on either side of central maxima. Central maxima. For that purpose, we assume that suppose the width of a slit, is small a, is in order of millimeter, and distance between slit and screen is D. That is in order of meter. Is in order of meter. So as we do the diagram of, there is the slit, and here the screen is this. There is the screen. There is the perpendicular bisector of a slit. Now as we do the central maximum, so central maximum is like this way. So there is the central maximum. Now from the slit, there is the angle theta. So this angle is also theta. So there is the first minimum. There is also first minimum. And that is the central maximum. Therefore, the width of a central maximum is the distance between the first minimum on either side of the central maximum. That is the slit, and the width is A. And the width is A. Now this distance is the B0 or the beta 0. That is the linear width of central maximum. Is the central maximum. The distance between the slit and skein, there is a skein. This distance is B. Therefore, the minimum of one side of a central maximum, the width of minimum on one side of a central maximum is theta is equal to lambda upon lambda upon. Already we know this thing. That is the equation 1, where theta is half width of angular width of a central maximum. Therefore, the angular width of a central maximum is 2 theta is equal to 2 lambda upon E. Now listen, here in figure, so this distance is D, that is angle subtended is theta, that is the first order minimum, that is the central maximum. Now theta is the half width of the total angular width of a central maximum. Therefore, total angular width of the central maximum is 2 theta is equal to 2 lambda upon A. That is equation 2. Now from figure, angular width of a central maximum is angle 2 theta is equal to I upon radian. Here we consider that this point of a slit as a center as we do the circle. Actually here the D distance is very large compared to the width of a slit, that is in order of meter, while the width of a slit is in order of millimeter. Therefore, this portion is the arc, and actually here angular or the linear distance. So it's equal to beta 0 upon D. Beta 0 upon D. Therefore, linear width of a central maximum is beta 0 is equal to 2 theta into D. 2 theta into D. That means the angular weight into D. Angular weight into D. Angular weight is 2 theta into D. From equation 1, substitute the value. From equation 1, theta is equal to lambda upon A. Therefore, beta 0 is equal to 2d lambda upon A is the linear width of a central maximum. That is the beta 0 is equal to 2d upon. So here we start from this. The width of a central maximum is the distance between the first minimum on either side of a central maximum. Now, as we assume that suppose the width of a slit is A and the distance between the slit and screen is capital B. Here the small a is in order of millimeter and capital B is in order of meters. Therefore, width of a minimum on one side of a central maximum, theta is equal to lambda upon A. Already we derived this equation. Theta is equal to lambda upon A. Therefore, the theta is what? The half width of the angular width of a central maximum. Therefore, total angular width is theta plus theta. That means the 2 theta. 2 theta is equal to 2 lambda upon. Now, from figure, the angular width of the central maximum, from the definition of angle in radian, theta is equal to I upon radius. I is beta 0 and radius is d. Therefore, 2 theta is equal to beta 0 upon d. Therefore, the linear width of a central maximum, beta 0, is equal to 2 theta into, here, beta 0 is the linear width of a central maximum or the distance between the first minimum on either side of central maximum, where beta 0 is the linear width of a central maximum. Therefore, linear width of a central maximum, beta 0 is angular width into d. Angular width is this. Theta is equal to lambda upon A. So 2 times, so 2 lambda upon A into d. Okay, now after that we obtain the linear width of a central maximum. Now we are going to derive the equation of linear width of nth order secondary maximum. For that purpose, the angular width of nth order secondary maximum is the distance between angular distance between n and n plus 1th order minimum. The angular width of nth order secondary maximum is the angular distance between n and n plus 1 minimum. N and n plus 1 minimum. Now first understand what that says on a screen. Suppose here nth order maximum is obtained, nth maximum. So this side is nth minimum and that is the n plus 1th minimum. N plus 1 minimum. So this distance gives the width of a nth order maximum. For that purpose here, the angle of nth minimum is theta n is equal to n lambda upon a. Already we obtained for the first minimum or the width of the first minimum on one side of central maximum is lambda upon a. Here nth minimum, therefore n times lambda upon a. And the angle of n plus 1 minimum is theta n plus 1 is equal to n plus 1 lambda upon a. Therefore, angular width of n secondary maxima is difference between these two angles, theta n plus 1 minus theta n is equal to n plus 1 lambda upon a minus lambda upon a, n lambda upon a. So we obtain the lambda upon a only. Now, linear width of nth order secondary maximum is beta is equal to angular weight into d. Now angular width we obtain, that is the lambda upon a into d. That means the lambda d upon a. That is the linear width of nth order secondary maximum. But we know that linear width of central maximum is beta 0 is equal to 2 lambda d upon a. There is equation number 2, there is 1. Taking ratio of equation 2 and 1. Therefore, beta 0 upon beta is equal to 2 lambda d upon a upon lambda d upon a. That is cancelled only 2. Therefore, beta 0 is equal to 2 beta. That means the width of central maximum is double of width of nth order maximum. There is. So there is the equation of linear width of nth order secondary maximum.